Hello everyone, my name is Kumar Aditya, and in this video I will show you the simulation of asymmetrical duty cycle control of single phase inverter. So this is yet another control method used in the control of high frequency single phase inverter, and its application is mainly in the load resonant type of converter. So if you see my plot window, this last plot is showing the typical output waveform obtained using this type of control strategy. And to generate this type of wave shape, I'm showing you the getting signal of my four switches. So top plot is showing the getting signal for switch M1 and M2, that is the switches in leg A of my inverter. And in the second plot I'm showing the getting signal for switch M3 and M4, that is switches in leg B of my inverter. And you can notice the both leg are switching at the ratio of 75 to 25%. So if my duty cycle is currently set to 25%, which means that my M1 and M4 is switching at 25%, and M2 and M3 is turning on and off at 75% of the switching time interval. So this is how essentially it works, and you can understand that M1 and M4 getting signal for M1 and M4 will be of equal width, because inverter needs to switch M1 and M4 for this flow of current in this direction, and then M3 and M4 for reversal of current to generate AC output. So fairly simple to implement. VC is my carrier wave. So let me just put another plot window here. So this is my ramp signal, and D is the duty cycle. I'm generating these two pulses and feeding them into this network here, which mainly consists of two comparator, and that's it. That's all you need to generate the logic for controlling this inverter using asymmetrical duty cycle control. Rest of the circuit here is just to implement dead time. So I have given the formula for the dead time here. By varying the R and C in this circuit, you can vary the dead time interval between the complementary switches of leg A or leg B of this inverter. So one comparator is generating one gating pulse, and from that gating pulse I'm using this network to generate complementary pulses with dead time of 0.7 microsecond. Similarly, second comparator is generating the gating signal for another leg, and this gating signal is fed to this network to generate two complementary pulses for switching the leg B with certain dead time. So fairly simple to implement, and one thing to notice here is that in this control you can vary the duty cycle from 0 to 100%, and your output voltage will go from minus VDC to full VDC. So let me just show you what happens if I keep my duty cycle to 0. Just observe the output voltage. You see my output voltage is minus 40, which is the DC link of this inverter. And what happens if I make the duty cycle to 1? So see, output voltage stays constant at 40 volt. So by varying from 0 to 100% duty cycle, you are essentially changing the output from minus 40 to 40. And intermediate stage is will give you the AC kind of wave shape with positive and negative half cycle. So let me show you the waveform for 50% duty cycle. So you see this is the output voltage for 50% duty cycle, and it is very symmetrical. It is the only duty cycle at which the output voltage have equal positive and negative half cycle pulse width. For rest of the duty cycle, your wave shape is highly unsymmetrical. Let me also show you the load current. So you see the load current is sinusoidal. This is because my load is a RLC load, and I have tuned it to the switching frequency to work as a load resonant converter. So that's it. If you have any question, please leave that in the comment section, and I will talk to you in the next video. Bye bye.